Okay. Hello everyone. Welcome to IGCSE Maths ZNotes Live. My name is Devandhira, and some of you guys may know me as the Pierrat from the Discord server. And today we got a special guest, Ivan Zelich. Welcome, and please introduce yourself.
Thanks, Devan. Yeah, so as Devan said, my name is Ivan Zelich. I just graduated as a master's student from the University of Cambridge, doing mathematics. Today the idea is going to go through numbers. Let's get right into it. So the kind of overarching theme in this little lesson will be about ratios. So we'll go through kind of first the properties of numbers, HCF, LCM, and stuff like that, and then we'll go through ratios, percentages, and then we'll go through some problems at the end. How does that sound, Devin?
Yeah, that sounds great. Let's get into it.
Awesome. Okay. So first we'll go through some concepts that will probably appear on the exam in some shape or form. So first off, we're starting with the notion of sets. So sets are just a collection of objects, and you could have any set, like a collection of fruits, apples, oranges, pineapples, or whatever. And some fruits can also be vegetables. So if you had well, not really, but some of us are a bit confused sometimes. So if you had like another set of, say, vegetables, and then we had an intersection of fruits that could be vegetables but aren't, and stuff like that, then that's what we would call the intersection of two sets. So sometimes it's nice to write it as a Venn diagram. Here we have A is some set and B is some set, and then we intersect them. So A is the set of natural numbers. These guys are the integers greater than 0, and B is the set of natural numbers between A and B. So the intersection will just be the set of natural numbers between A and B. And yeah, so that's kind of how this works. But the concept of a set is quite intuitive, so we won't focus much on that. Does that all make sense, Devin?
Yep, sounds great.
Awesome. Okay. Let's move on. So this is another example of kind of a set. So as we said, you can represent it as like a Venn diagram, but in this sense, we have like very much containments of every set. So the natural numbers are integers greater than 0, so they're inside the integers. Rational numbers, obviously, these guys are like your fractions, and they contain the integers as a subset. So this increasing union of different sets, and yeah, but don't worry too much on this. Like, this is kind of abstract, but it's very intuitive. So I think we'll move on to the more important concepts now. Okay.
Yep.
So I guess this is our first kind of important concept to note. So prime factorization is very important. The natural numbers are built up of primes. Primes are the guys that cannot be broken down, and the other numbers can be broken down into these guys that can't be broken down. So then we end up with a prime factorization. So here we have a prime factor tree, I believe it's called, of 48. And we can see that 48 can be written as 2 to the 4 times 3. I've also included another factor tree here of 36. And so here we see 36 is 2 squared times 3 squared. And so now we would like to calculate the HCF and the LCM. So with HCF as the highest common factor, so when you're going through the exam, just make sure that that's smaller than both numbers, or at least, it has to be smaller or equal to both numbers. And the highest common factor should be greater than or equal to both numbers. So as a sanity check at the end, just make sure that actually happens. So here we have, I've just written out kind of the prime factorizations. And so to find the LCM, you take the largest of the exponents of each prime. So 48 has an exponent of 4 on the 2, so we take 2 to the 4. And 36 has a squared on the 3, so we take 3 squared, and then the LCM is 144. The HCF is you take the smallest exponents. So in this case, for the 2, it's 2 squared, and for the 3, it's just 3 itself, and that gives you your HCF. Is that all good, Devin?
Yeah, so the LCM you take the highest exponent, while the HCF you take the lowest exponent. Is that correct?
Exactly, yeah.
Okay, sounds great. Let's move on.
Yeah. And also one important thing, Devon,
Yes.
is to note that if you had like another prime factor lurking in, like for example, 48 has 5 to the 0 in it. So just remember that like if all the other primes, like when you take into account the highest one and the lowest one, the ones that don't have that prime is going to be 5 to the 0 or 7 to the 0.
Okay. Okay.
So maybe it's sometimes useful to write that out just in case.
Okay. Makes sense.
Okay.
Right.
So now let's move on to these guys, indices. So I think one of the reasons indices are really important is in science, and I think this is one of the reasons why they appear. So let's say you were kind of trying to measure your height and you had a 1 meter ruler, then the degree of accuracy a ruler is I believe usually in centimeters. So when you measure something and then say your height was 179 centimeters, and then you divide it by 3, and then you had 100 and well, when you divided by 3, you had 59.66667 or something like that. The degree of accuracy is still going to be in centimeters. It's not going to have those decimal points, because your ruler can't measure that specifically. So the reason these things are important is mostly because of science, to stipulate what degree of accuracy you have when you're doing an experiment or something like that. And so when you do the calculations, you've got to take into account that. And so here we have an example. This is a different type of thing, limits of accuracy. So it's quite similar. So in this case, the distance from home to school is 27.5 kilometers. And so because we have a 0.5, our accuracy is to 1 decimal place. And so, but when we measure it, it could be either plus 0.05 or minus 0.05. We don't know because the way you measured it might have been a bit off with the way you're doing it. So we give a little limit. And so this is the reason why we have our distance can either be 27.45 or 27.55 and anything in between based on how well we measured it. So does that make sense, Devan?
Yeah, sounds great. So if let's say something is measured in 2 decimal places, then that means you have to do the plus minus in 0.005.
Exactly, yeah. So
Okay.
yeah, always half of that kind of degree. Yeah. So yeah.
Okay. Makes sense.
And this general principle is quite good. However, when you get into later on, if you do study like physics, you learn better ways of measuring kind of your limit of accuracies. But this is like a universal way of doing it.
Okay.
Yeah.
Sounds great.
Okay. So ratios and proportion. Right. So I believe we all kind of have an idea of what ratios are. So we have an example here. If we have 1 red ball and 2, I guess they're marbles, and 2 green marbles, then the ratio is 1 to 2, obviously. But 1/3 of them are red and 2/3 of them are green. And we'll see this in an actual problem to get our hands dirty. But this is kind of the idea. It's quite intuitive. If you count, say there were 3 and 5, then the ratio is 3 to 5, and it's 3/8 and 5/8 of the proportion. But we'll go definitely more into that later. So there's also these notions of direct proportion. So let's just kind of give an example. But the universal idea here is that we have 2 quantities, or 3 or 4, and so say 2 quantities. Say we had well, we'll give an example, but 2 quantities, if this quantity increases and the other quantity increases, then they're kind of in direct proportion. Now, they might not be exactly in direct proportion, but that's the kind of the key idea behind it. If one increases and the other increases, an inverse proportion would be, say, one increases but the other decreases. And then there you would have an inverse proportion, but you'd have to really check if it was exactly, a line or a hyperbola in the inverse proportion case. So an example would be, say you were running, you had a car going at 60 kilometers per hour. So obviously, as you go forth, you are kind of the more meters you go, the more time it'll take to reach those meters. So if you go 100 meters, it'll take some time, and then 1,000 meters, it'll take more time. And these are in direct proportion. On the other hand, if you are, say, if you are kind of going at a fixed distance, say 100 meters, then the speed at which you go and the time it takes to finish the 100 meters will be in inverse proportion, right? Because if you're going faster, the time taken is less. If you're going slower than the time taken is more to complete the track of 100 meters. So this is kind of an idea of what these guys are. Devan, do you know if if the direct proportion and inverse proportions actually, does it pop up much in the exam?
It pops out quite much in paper 2. In paper 2 IGCSE Maths. Yeah, it usually comes out.
Yeah, so I guess one thing that's important to note is in this case that to verify if something's in direct proportion, you need to show that it lies on a line, as you can see there. And so you need to make sure that y on x is some constant. And for direct proportion, it'll be y times x is some constant. And if you can show that, then that would be in direct proportion. And so, yeah, direct proportion is usually a line through the origin. That would be a key way of verifying that. Okay. Is that all good? Should we move on?
Yeah, but I would like to also point out an example for direct proportion. It's like from my real life example. I usually, when I cook rice, you need more water if there are more rice. That's basically directly proportional. Yeah. And also, another example for inversely proportional is, say you're painting a house. If you hire more painters, then the time taken would be less. Yeah. So one rises, one goes down. Yeah, that's basically inversely proportional. Yeah. That's
and
it.
I think in that case too, for it to be inversely proportional, you would need the people that you get to work at the same rate. Because if there were different rates, then suddenly you wouldn't have the exact inverse proportion, but it would still go down and up. Yeah.
Yeah. Yep.
Okay.
That makes sense. Let's move on.
Okay. Cool. So okay, percentages. So I like to kind of point out that percentages are really ratios, but that are out of 100. I mean, this is the first point there, but it's really important. So essentially, the point is when you have a ratio, you have a percentage. Just you have to make sure that ratio is going to be out of 100. And so we'll see more examples of that, and I've tried to make that very clear. So when dealing with percentages in general can be quite annoying because they are out of 100, and so when you're doing calculations of them, you have to make sure of that. Or when you're with ratios, generally, because it's already out of a ratio, then you can very easily keep kind of track of what you're doing. So we'll see that later on, though. Percentage increase and decrease. So I guess we'll see examples of that to kind of make sense. But if you had, so if you had $100 and then suddenly you got $110, you got $10 from a mate, then the change will be $10 and the original amount's 100. So that is 10 on 100 times 100, which is 10. So 10% increase. Very simple kind of calculation there. Simple interest. So I guess with interest and compound interest, it's always important to remember what they really mean. The formulas themselves can be kind of derived very quickly. It's useful to remember them, especially if under GCSE where you have time conditions. But when you are studying, it's very good to kind of understand why the formula is true, at least on a basic level. So with simple interest, in this case, you have a principal amount, 200, and your rate is 3%. I guess that would be how much interest you have on that. So 3% for 2 years. And the key with simple is that it's constant, so it doesn't increase. So if the 1 year you had $6, then that would be every time, and you just get that total interest. But compound interest is a bit different. So with this one, your kind of ratio, the amount increase changes, gets bigger or less every kind of year. And so in this case, we have compound interest example. In year one, the interest was $6, but year two, the interest was $6.18. And so that's the kind of key difference between simple and compound interest. Is that good, Devon?
Yeah, that sounds good.
Yeah. We'll see definitely more of an example. And this compound interest is a key formula to remember, and we'll actually derive it later on. And so then you'll have two kind of ways of doing the same problem. One where you don't use the compound interest formula, but you kind of do it yourself, and the other you kind of you could use a compound interest formula, but we won't because you can't use it directly from here. But we'll see it more later. Anyway, enough talking. Let's get right into some problems. So, first problem: the price of a newspaper increased from $0.97 to $1.13. Calculate the percentage increase. Right. So step one is always when you're doing a problem is to figure out what the problem's asking. So in this case, percentages are just ratios. So this is why I've said it's essentially a ratio problem. And I've given an example here. So if instead I told you the newspaper was $100 and it increased to $150, then the percentage increase would be 50%. So our strategy will be to make 0.97 to be 100 and then find the corresponding value of 1.13. So to do that, we're going to multiply everything by 100 on 0.97. And so 0.97 will go to 100 because we made it that way. And 1.13 will go to the corresponding value, which is 1.13 times 100 on 0.97, which is 116.495. And now the percentage increase is very simple. We simply take the two values from each other, so 116.495 minus 100 is 16.495%. And because dollars are always in two decimal places, we need to round up. And so we get 16.50% is the percentage increase. I guess, it's always important to know when to do the conversions, and perhaps we should have done the conversion earlier, but in this case, it didn't actually make a difference. But in general, when you're finding the price of something, you will always round up it as early as possible.
I'd like to point out too, and when in IGCSE, your final answers must be rounded off up to three significant figures. That's why the answer is 16.5%.
Yeah. Okay, cool.
That's it.
Right. Okay. Next question.
Let's move on.
Okay. So we have one day the newspaper had 60 pages of news and advertisements. The ratio of pages of news to pages of advertisements is 5 to 7. Calculate the number of pages of advertisements. So again, this is a ratio problem. We're given a ratio, so we expect it to be a ratio problem. Now, again, when we're having a problem, we want to kind of step back and think to really understand what we're doing. And so if we had counted 5 newspapers, so I just took the newspaper and there was 5 newspapers, then because of the ratio, I know there have to be 7 advertisements. Now, in those 12 pages, we expect there to be 5 newspapers and 7 advertisements. And of course, with any ratio, 12 is not a random number, it's 5 plus 7. So if it was 2 to 3, it'll be 2 plus 3. Okay, so we know for every 12 newspapers we have 5. We have 5 news pages and 7 advertisements. So now we know we have 60 newspaper pages. So we're going to make 12 to be 60. To do that, we multiply by 60 on 12. And in this case, that's just 5. And when we do that, we get, so the number of newspapers would be 5. So 5 times 5 is 25. That's how many is in 60 pages. And then 7 times 5 would give you 35 advertisements. How does that sound, Devan?
Yeah, that makes sense.
Cool. So when you do it this way, it might be a bit different, but it really helps to figure out what ratios are. If you have 5 on 12, that's the same as just 25 on 60. And the reason is because we've learned this a lot. It's about simplifying fractions. Yeah, but its simplest form, but you can also have it in different forms. And That's one way of looking at these types of problems. Now, part B, because of how we did part A, we can very simply kind of calculate the percentage increase. So we have 25 newspaper papers. So newspapers. it's a bit of a pages. Okay, there we go. Newspapers. And we have 25 news pages. We make that to be 100 because remember, percentages are ratios out of 100. And so that's by multiplying by 125. So that's just 4. And then we multiply 35 by 4 and we get 140%. And that's how the percentage would work. Sound good?
Yep, all good.
Okay, next problem. So now we have part C. And part C is Maria paid 2.25 euros for the newspaper when the exchange rate was $1 is 0.9416 euros. At home, Maria paid $1.13 for the newspaper. So now we have to calculate the difference in price, and we have to give our answer in dollars to the nearest cent. So as always, we will step back and figure out what we have to do. And these sorts of problems, it's also good to figure out roughly what the answer should be. So this question asks us to give our answer in dollars. So we need to figure out how much is 2.25 euros in dollars. That's the first thing we should do. And to do that, we've given a ratio. We know $1 is 0.94616 euros. So, as always, our goal is to make this ratio bigger in order to find what the corresponding dollar is. So we'll make 0.9416 to be 2.25 euros. And that conversion rate is 2.25 on 0.9416. Okay, and now of course, we just have to do everything to both sides. So we know $1, we multiply $1 by our conversion, which is 2.25 on 0.9416, and we get 2.3895. So this is how much Maria paid in dollars. And so we now have to put that to two significant figures because, I mean, dollars is, you don't have any better accuracy than cents. So we that's just $2.39. And the difference will be 2.39 minus 1.13 is 1.26. Sorry, there's a little typo there. But yeah, so the difference is 1.26, and that's our answer. So what I wanted to quickly just say is that from the get-go, we know about 2.25 euros. So the euro is stronger than the dollar. So we know that roughly how much she paid would be even greater than 2.25. So if she paid at home 1.13, we do expect her to have paid more. So that's one way of kind of just making sure you're correct in the general idea of the problem, because procedure marks are quite important, I think, in GCSE. Is that right, Devan, or is it?
Yep, that's correct.
Yeah. Cool. Is there anything I could have explained better here that you want me to more on?
No, nothing. It's just that it says the significant figures is 2, but I think it should be 3, right?
Well, I mean, you know best, Devan, I guess, with the GCSE. However, from what I would think is that if you're paying in dollars, in general, I would say 3, but maybe in this case it would be better to put 2 because, I mean,
this is 2 decimal places, right?
Yeah, because it's dollars. I mean, yeah.
Yeah. Makes sense.
It's in problem solving, these things are real life scenarios in general, so it's good to be as realistic as possible, I would say.
Okay. Yep.
But yeah, in general, I would say 3 is a standard.
Okay.
Except when it's in dollars and it's real life, then it's like, okay, maybe better. Yeah. Okay.
All right.
So now we have our last problem. So okay, cool. The newspapers sold decreases by X% each year. Over a period of 21 years, the newspapers sold decreases from 1,763,000 to 580,000. So 1,763,000 to 58,000. Calculate X. Okay. So this is one example of what I say. This is very much like a kind of compound interest type problem, except compound interest goes up. Well, in general, we want to decrease here. So the only difference is going to be a matter of a sign, and we'll see why that comes out. So again, when we have problem solving, we want to stop and think. So as we said, percentages like ratios, so we just want a ratio. And so I've given an example here. So if we had 100 newspapers and X was 10%, then we would end up with 90 newspapers next year, and then the ratio being 9 on 10. So if we multiply 100 by 9 on 10, we get 90. So in general, we can calculate what the ratio of decrease is from a percentage, and that would be 100 minus X on 100, which is 1 minus X on 100. So if we go back quickly to the compound interest kind of formula, the only difference we have is that, oops,
too far.
Sorry, it's a bit of a lag here. Yeah, so the only difference here is that, we have a 1 plus R on 100, while in our problem we have 1 minus. This is the only difference. So if you just wanted to plug and chuck into the compound interest formula, you could. However, you'd have to make sure that you knew it was a minus, not a plus. Okay? So let's quickly go to the end. Hopefully it'll be quick enough to just do that.
Yeah, it's okay.
Okay, are we there? Are we too far now?
Oh, a bit too far. Okay, there you go.
Now? Okay, cool. So, yeah, so this is it. We just have a ratio as 1 minus X on 100. And so our question is telling us that if we start with 1,763,000, we multiply by this ratio of decrease for 21 years, we will get 58,000. Okay? And now we want to solve this equation. So we have to continue, we have to use BODMAS. So basically, we divide by 1,763,000, we get that ratio of what 1 minus X to the 100 is. So we have to kind of keep our surd on one side in order to continue. And then we take the 21th root. We can do that on a calculator. And then we do 1 minus on both sides. We get X on 100 is this, and then multiply by 100. And so what we end up is 100 times that big expression, and plug that into calculator and we get 15.01%. And that's it. Not much more to it. So yeah, as I said, you could have done it with the compound interest formula. However, obviously you can't just blindly follow it. You need to make sure that you realize it was a decrease, and so your ratio would have to be 1 minus X on 100, not 1 plus, and then everything will be fine. Is that all good, Devon? Anything else you want to say on that?
All great, all great.
Okay, cool. So I guess that's it. We went through, so to wrap up, we kind of discussed a few key concepts, but the primary focus of this one was ratios, because I guess they'll appear everywhere and you have to be prepared for that. Always is a good thing in ratios is to just understand what a ratio means and being able to convert kind of one ratio to another in order to figure out certain problems. But other than that, it's all about practice and making sure you understand the key concepts. And yeah, I guess that's it from us. And we'll see you next week.
All right.
We'll discuss geometry.
So thank you, Ivan. And then that's it for today. Next week we'll be dealing with algebra and graphs. And yeah, that's it. Thank you for joining us today. Please check out our Instagram page and server. Come talk to me or Ivan. You can always talk to me. It's fine.
Yeah, we're available anytime.
That's it. Thank you for watching.